Here's week 9 notes. It very much continues just what we did in week 8 when it comes to intermolecular forces, but it also is going to include some tougher stuff at the end that will need practice. And your unit test is on Tuesday, 11/11. So we said in the last slides that dispersion is the weakest, dipole is stronger, hydrogen bonding is strongest among molecular compounds, and then ion dipole is the highest. Dispersion only occurs between all molecules, but if you are nonpolar, that's it. Polar compounds will have dipole, and then polar compounds with a hydrogen and a NOF, and those are the strongest. However, notice how there is a plus here, and there seems to be a limit with just hydrogen bonding. So these top two dispersion dipole can make the intermolecular forces stronger than everything if there's enough of them. But if that statement didn't make sense, just sort of ignore it for now and just know that it goes in that order. So we said as dispersion forces increase, so does boiling point or melting point. Saw that in the lab. And then I guess you see this graph now, and so we see that again. And that's just because there's more protons and more electrons, especially electrons, that then can be attracted to the protons of another, so xenon. So the two reasons why xenon, those electrons are further away than the protons, so therefore there's less attraction between those electrons and those protons in the middle. Then those electrons have a better chance of being attracted to the protons of another xenon element because there's so many electrons and there's so many protons as well. How it's normally taught is just there's more electrons that therefore that moment of dipole where the other electrons are not in the way, it just has a higher chance. Here, these are all nonpolar compounds. So if I were to draw these out, it's going to be just a long carbon chain with hydrogens on the side. And because those are symmetrical, those are all they just have dispersion forces. So therefore, as for the molar mass, the boiling point to go up, the molar mass has to go up. So here we have pentane, like C5H12, up to nonane C9H20. You just have more carbons and more hydrogens, therefore more electrons that will therefore have more dispersion forces. So we see here something that would be important that I know I'll ask is, even though I think it's heptane or which one. So heptane has a boiling point of 100 and so does water. So you can say that heptane's dispersion forces are as strong as water's dispersion, dipole, and hydrogen bond. And again, as size increases, and the electrons get further away, so does the boiling point and melting point. So here, the thing that is closest to the bottom, these are all halogens. And the thing that's closest to the bottom is bromine. So bromine is going to have the highest one, has the highest dispersion. And fluorine has highest LDFs. So all of these are just nonpolar. This is the lowest LDFs. So like fluorine, even though it's the strongest at tug of war, if it's playing someone just as strong as it, like a clone of it, no one's going to win. So that makes it nonpolar. So any of that polarity doesn't matter here. And so it's just dispersion forces. Then we go with the size, and then we know as we go down the periodic table, you get larger. So here are two compounds that show what I'm trying to say here. So ethane just has LDFs. Formaldehyde, everything always has dispersion forces or LDFs. They both have the same molar mass, or you can say they have the same molar mass, close enough. But then the boiling point and melting point for formaldehyde is much higher. And that's because ethane, being a nonpolar compound, just has dispersion forces, while formaldehyde is a polar compound, and therefore it has dipole forces as well. But it doesn't have hydrogen bonds because both those hydrogens are connected to a carbon. But here, the reason why formaldehyde has a higher melting point and boiling point is because it has dipole bonds. They probably have this very, very, very similar amount of dispersion forces. So here I have three compounds, and I go, which one of these has the highest boiling point? So we know if it has more intermolecular forces, it's going to have a higher boiling point, higher melting point. So CO2 just has dispersion. All of them have dispersion. Then the only one that is not symmetrical or will experience a dipole in that direction, because chlorine has a higher electronegativity, is going to be the middle one. The rest of them are done. So this has the highest. Then we can look at the next two and really just use molar mass, because protons and electrons are equal to each other. Protons is what determines mass. There's a big part of half of what determines mass, and then so molar mass of CH4 is 16, CO2 it is 32 plus 12, that's 44. So the lowest is going to be CH4. Then we have one like HF and HCl, and both have dispersion, both have dipole. And what's interesting is a student brought up in my 9 a.m., if you had to stop right here, you would think HCl has a higher boiling point than HF, because Cl is bigger than F, Cl has more electrons than F, and like, I don't know how I would word this question, but I'll be like pretending there's no such thing as hydrogen bonds, which would have a higher boiling point, and it'll be HCl, because it has more dispersion forces, and they both have dipole. So, however, HF has a greater dipole because fluorine has a very high electronegativity and therefore has H bonds. It has H bond and a hydrogen not connected to a carbon. So HF is going to have a higher boiling point even though HCl is heavier than it, and even though HCl has greater dispersion forces. So again, we can look at these three compounds. All have dispersion. Then the first two have dipole. And then the only one that has H bonds is that methanol, CH3OH. And so methanol, because that has a hydrogen not connected to carbon and a fund, methanol is going to have the highest boiling point. And that makes sense if we were to look at molar mass. 28. So like really, methanol here has barely a higher molar mass than carbon monoxide. But we all know carbon monoxide is a gas. I know because about a year ago it almost killed me 12 nights in a row. But while methanol is a liquid, but even though their molar masses are very similar, um, methanol is a liquid at room temperature, and carbon monoxide is a gas, which I know again because it killed me 12, almost killed me 12 nights in a row. Note, during those 12 days, I didn't miss one class, and I almost died every single day. Now, I don't know if I should be bragging about that because I probably should have just figured out what was going on. But anyways, I put an asterisk next to all of the nonpolar compounds. And I'm going to give a graph similar to this, in fact, maybe the same. And I have an asterisk next to the nonpolar ones. Notice how they have very low boiling point, and as we go up in mass, the boiling point goes up. Then ones that are polar, let's forget about water for now. Ones are polar that have similar molar masses have much higher boiling points. So if that didn't make sense, like listen to it again, because I don't know, I'm going to be a little more clever with this question than I was last year. The outlier in this is water. So they keep going up as we go down. So for example, if I look at these three polar ones, it goes 32, molar mass 32, 46, 60, and the boiling point goes higher. And those are all polar, but water has the highest of all of these. And the reason for that is, let's see if I write in my next slide, I do not, but water forms two hydrogen bonds because it has multiple lone pairs, and then those hydrogens, it has two hydrogens on it, they're not connected to a carbon, compared to methanol, which has just one hydrogen on it that's not connected to a carbon. So water forms twice as many hydrogen bonds. So that's why water's boiling point and melting point is very high. It's very hard to boil water. Like if you want to make ramen noodles, like I want to make ramen noodles all the time because I don't know, that's what I got. And you know, I put water on the stove. It takes forever to boil it, you know, so water has a high boiling point. All right, as intermolecular forces increase, so does boiling point and melting point. Usually, why usually? I forgot what I did in class with you for this. Dispersion usually. So let's just see what I'm talking about in the next slide. I don't remember what I did. All right, so here, what I was trying to say is, if we look at all of these, so these just have dispersion forces. Then this has H bonds, and this is dipole bonds. However, we see some with just dispersion greater or very close to ones with H bonds and ones with dipole bonds. And that's because this dispersion octane there is heavier than hexanol and hexanone. Or a better way of saying this is, let's just say we ignore these here. Hexane, hexanone, and hexanol, dispersion, dipole, H bonds. We see that with dipole, the boiling point goes up. With H bonds, the boiling point goes up. However, if we were to make a larger compound If we're continued to make larger compounds like the one above, like nonane, which is 10 or 9 carbons, then we could probably predict that that boiling point is going to be higher than something with H bonds. So again, if that didn't make sense, probably rewatch that and make sure you follow. So now we're going to look at solubility rules. And solubility rules you will be given, but they all are related to salts. Like, and a salt is an ionic bond. An ionic bond is a metal and a non-metal. So NaCl. Look at how all these sort of look like NaCl. Ask which one of these are NaCl. I don't know, you might be able to guess. But you probably get it wrong because I don't think anyone would guess that one. And so some salts dissolve in water, some do not. And that's what we're going to look at. So what I just said, some salts dissolve. So for example, NaCl, when you put it in water, it breaks down to this compound compared to MgO. And so here I'm just going to point off, okay, we have solid. So you take solid, you put in water, aqueous, aqueous. And but you did a lab earlier where you tried to dissolve MgO in water, see if it made a solution. And then if it made a solution, measure the conductivity. And MgO did not dissolve, and therefore had a low conductivity. However, I'm just relating this to a test question that a lot of students get wrong. When dissolved in water, ionic compounds always make the water very highly conductive. But I'm just sort of trying to relate that to a lab. Because you did this and there was like no reaction, it became a colloid or a suspension, and that was no reaction. So some salts do not dissolve in water. So you'll be given these rules and you'll have a lot of homework to practice on. And we're going to look at how to write some of these dissociation reactions and how to use those rules for determining whether a salt dissolves or not. If a salt does not dissolve, it's no reaction. If it does dissolve, you have to write out this dissociation reaction. So it disassociates from each other, dissociation reaction, using the rules that we have. So that first one, NaNO3, if you pull up the rules, it says Na. So you usually just want to look at the second one, and you can for this one as well. So maybe I'll just teach it that way. But like it says nitrates or NO3s are always soluble. Then, and there's no exceptions. Then this one says PbCl2, it says Cl, it says generally insoluble except in these occasions. And therefore that is not going to dissolve. So I'm going to write no reaction. The next one is a good one because it's a little bit harder to write, and it has ammonia, which is a polyatomic ion. It has carbonate. If you look at carbonate, it says insoluble other than with, I should have the rules in front of me, but I don't, but I'm pretty sure it says NaCl, or no, NaLiK, then NH4. So here this is soluble. So you have to first determine if it's soluble, and then you have to write out the equation. I'm going to go do these on the next page just for so I can write them out more clearly. So I'm going to write a bunch of these examples out and first determine if they're soluble or not. So one was FeOH3, Next one was K2SO4, then BaSO4, AgNO3, CaOH2, Li3PO4. All right, so look at the solubility rules and think to yourself, well, is it soluble or not? For FeOH3, I'm looking for OH minus. It says OH minus, compounds generally containing the following are insoluble when paired with, it's slightly soluble for some. If it says slightly soluble, I'm not going to give you any, but it's going to be insoluble. Alex doesn't give you, or your homework doesn't give you any anyways. But it says FeOH3, so OH is insoluble, and so this is going to be no reaction. Nothing happens. You're going to put it in water and nothing's going to happen. K2SO4, that is, so again, we're pretending like it's a solid because you're going to try to dissolve in water. Put K2SO4, which is an ionic compound, which is a salt, into water. And if we look at SO4, it says they're generally soluble except for with strontium, barium, Pb, Ag, so lead, silver, calcium. So here, this is going to break down, and it breaks down into its ions. And we have two potassiums. Potassium always forms a +1 charge, and the sulfate is SO4 2-. That charge is always going to be the same around those atoms. You get the polyatomic ion sheet and you get the solubility rules. So therefore, you can always refer back to those and just copy or like reproduce what it says as the charge, and then make sure that it's balanced in the sense that if there's a 2 down there, you need a 2 in front. Barium sulfate, in the same set of rules, it says sulfate is generally soluble except with strontium, barium, lead, and so this is going to be no reaction. That's not going to dissolve. Compared to the next one, Ag, I look for nitrates, and it says nitrates are always soluble, no exceptions. Remember, Ag is always a +1. If you forget that, again, that's on the polyatomic ion sheet. And then calcium hydroxide, it says OH is generally insoluble. When OH pairs with calcium, the result is slightly soluble. So we're going to say no reaction here, but I'm just not going to give it to you. I'm not going to give you one that's slightly soluble. So like slightly soluble means like, I don't know, it's very small. You learn it in Chem 2, but it's like 1 in, I don't know, millions. So if you ask me, that's not soluble, but I won't give any slightly soluble ones. So CuS, I'm looking at S, and it says generally insoluble. And then copper, it doesn't have any exceptions with that, so again, that's no reaction. And then lastly, we got lithium phosphate. So if we look at phosphates, it will say something, something, something. So it says insoluble except paired with LiNiK plus NH4. So this does break down to lithium AQ PO4 3- AQ. So AQ means it dissolves. So practice those, ask AI for more examples because you're going to be given those, and it's not something students always do great on. Here I give you the answer key, which sort of points out, what I just said, and might take it from a different point of view, but it's using the same solubility rules. It's like here with calcium hydroxide, it is like, again, since it says slightly soluble, and then it gives, so I got this from AI, and it, what it said is pick one and be consistent. And so I'll be consistent in the fact I won't give you one that's slightly soluble. If you do take Chem 2, like, you'll get what I mean. So I'll do these demonstrations. I'll do these demonstrations in class. So now we have a the first homework associated with this, which can be slightly difficult, and we have to predict if a precipitation occurs, meaning will something fall out? Will a solid fall out? And I'll show you how we're going to do this. So I'm just going to have to remember this: ammonium sulfide and iron 2 bromide. Let's take a picture of these because I'm going to have to do all three. Right. So essentially what we're doing is we're seeing that we're dissolving 2 salts in water, and both those salts are going to dissolve in water based on the solubility rules. However, once they dissolve in water, will a precipitate form out because one of the cations bonds with the anion of the other one, which says it's a solid under solubility rules. So practice is what helps here. The first one is ammonium sulfide. So you have the polyatomics. If it ends in "ide," it tends to just be from the periodic table. So we would have to write those. And also they're on the solubility sheet, these charges are. So if you can read that solubility sheet, you're in good shape. And then iron 2 bromide. So we have to determine if a solid forms, a precipitate forms. So essentially a negative and a positive aren't going to form ionic bonds because a positive and a negative, and then the positive are always going to go first. So like if that Fe here bonded with that S, and you guys are pretty good at it this way, where you fill in, you know, the two things, whatever. And then we have to look to see if either of these will form precipitates. I'm going to look at the solubility rules. FeS, it says S is generally insoluble, except when paired with calcium, strontium, barium, and so this is going to form a precipitate. So this would be the formula of the precipitate, the empirical formula of the precipitate. So we will click yes. Then the next one we can look at is NH4Br. And if we look at Br, it says are generally soluble except with Ag, with silver, mercury, or lead. So this is not going to form a precipitate. So if we do this reaction, a precipitate will fall out, and it would be FeS. Let's try another one. We got nickel sulfate. Nickel's 2. Sulfate is a polyatomic, ends in 8. It does not end in "ide." We got manganese iodide. Manganese is a +2. Iodide is a -1. Positives aren't going to go together, so this is going to be MnSO4, and this is going to be NiI2. And we have to then determine if a precipitate will form. For that MnSO4, we'll look at sulfates. Sulfates, it says, are generally soluble except with strontium, barium, lead, silver, or calcium. So this is not going to form a precipitate. And then NiI2, if we look at iodine, it says generally soluble except with silver, mercury, or lead. That is not going to form a precipitate. So we would dissolve both of these and nothing would precipitate out. The last one. And for that, that was the last one. Okay. Whew. Good. But we have more. So I'm going to take a picture of these and so I can do them on. So again, here we're going to say if a precipitate is formed. So if a precipitate's formed, we're going to go yes. If not, no. Then if it is yes, we have to write something here. First one, sodium hydroxide, and A plus 1, hydroxide is OH minus, and then iron 3 sulfate, Fe3 plus, sulfate SO4 2 minus. All this stuff is on the sheet. Plus plus, negative negative, don't form. This is FeOH3. Oh, if we do this in the last one, I don't know. But then this is then Na2SO4. So writing these formulas takes practice. So I would suggest practicing. Yeah, but you know, same stuff comes up over and over again. So eventually, it's not going to seem like, oh, there's tons of different compounds or elements or whatever. You know, so OH, it says continually compounds containing the following ions are generally insoluble. OH minus is in there, and therefore, other than paired with those, so this is going to form a precipitate, which is that, and then sulfate that does not form a precipitate based on the solubility rules. The next one is ammonium nitrate, NH4 plus, nitrate is NO3 minus, potassium hydroxide K plus 1, hydroxide OH minus. So plus plus, negative negative, KNO3, and then NH4OH. Look at the solubility rules, and I'll promise you, well, I'm not going to promise you, but look at the solubility rules now and see that no precipitate would form if we mix these two. Last one here is potassium carbonate. And silver nitrate. Negatives and positives aren't going to go together. Ag2CO3. Now, why is there two? Because, well, the crossover method, and also you need, better way to say it is you need two silvers to cancel out a carbonate. And then KNO3. So KNO3 is going to be soluble. Nitrates are always soluble, and group 1 elements are always soluble. So but then let's look at the carbonate one. At the bottom it says carbonates are generally insoluble except with Li, NaK, and NH4. So this would form a precipitate, and that would be the empirical formula of the precipitate. Now, what happens in this reaction? So a solid forms. Oh, I see what I was doing. All right. Well, I'm trying to lead you into the next thing, and yeah, solid forms. Oh no, I see. Okay, so we got KBr and PB2 NO3. I assume it's yes because PBBr2, so it becomes like Br minus plus PB2 plus forms. Cation's always first. I'm going to balance that. That's AQ, AQ. And then if we look at the solubility rules, bromine is generally soluble except with silver, mercury, and lead. So this is what happens in the reaction. How I'm going to test it though is sort of the opposite. So it's called writing the net ionic equation, which again you'll get a lot of practice with your homework. And so the way I have this set up is sort of showing the real way, but writing the reverse sometimes helps you better understand what is going on. And so here is the reaction that you're going to have to do for your homework and then do later. And this is a net ionic equation, meaning if something dissolves, these two dissolve in water. and they're floating around freely. And two of them bond together and form a precipitate, meaning they form a solid. Like you have two literally clear liquids and something solid comes out. Those are the only things that really react in the reaction. So to write a net ionic equation, we're going to start at whatever the solid is formed and write what made it, because everything else doesn't matter. And so in this case, we know that iron hydroxide is formed. And what are the things that form it? It's going to be Fe, 3 plus AQ, and 3 hydroxides, AQ. So that's the answer. Now, how do I get that Fe3 plus? Well, we know a hydroxide is a -1, and we know that Fe is canceling out that hydroxide, and there's 3 hydroxides. So Fe would be 3 plus. Hydroxide is a -1, we know that because on both your solubility sheet and the polyatomic ions, it will say that. And we have a 3 in front because there's a 3 outside that parentheses. In a sense, if there's something outside that parentheses, then that should go in the front on the other side. One last question I'm going to ask is, what are the spectator ions? The solid formed, so the things that did nothing. So on the right there we have that Na2SO4. Those are the thing that the compound, or looks like a compound, that does nothing, are things just watching, like they're spectating in the solution. And so the spectator ions are Na plus and SO4 2 minus. Because those are the ions and those don't react. It seems like those two are bonded together, but really they're aqueous on both sides. Therefore, there is no bonding taking place. Let's try another one here. We're going to start off with the solid, so AgCl. This one is a little bit easier and maybe one I should have started off with. So if the last one didn't make sense, try this one first. AgCl, or try the last one after you do this one. AgCl is a solid, that's what precipitated out. Ag plus, what formed that? Aqueous, Ag, Cl minus, Aq, aqueous, and that is the net ionic equation. Now I'm going to go, what are the spectator ions? So what's on the right that does not form a solid? Meaning, what's aqueous on both sides? I've heard students say it like that. Like, I don't know if that's that easy to see, but it makes sense. Like something has aqueous in front of it on both sides. Here it's going to be that NH4 there, and here it's that NO3 there. And so the spectator ions are going to be NH4 plus. I don't know if you got to write that aqueous after, really. It doesn't matter. And then NO3 minus. Those are the ions. If you write NH4 NO3, that would be wrong. You have to write the ions because they're not bonded together. And all right, so that is week 9, I believe.